Okay, this is Paul Geyer, and I will be the presenter today for this webinar, An Introduction to Noise Control in Buildings. A little housekeeping issue to get started with. The way we will proceed is I move forward with the discussion for 50 minutes, then take a 10-minute break so people can answer their emails and that sort of thing. Come back, do another 50 minutes, 10 minutes, 50 minutes, 10 minutes, and just keep going through that cycle. Now, this is just a 2 PDH or 2-hour webinar, so I'll just be going through that cycle 2 times. This is, of course, an interactive webinar, and questions and comments are, of course, welcome and encouraged. I guess with this system, we've got a chat box and we've got a ask questions function. I kind of prefer the chat box. So if you just type your questions or your comments in to the chat box, I will be keeping an eye on that as we move along. Now, I want to place some emphasis on one word in the title of this webinar, and that is introduction, because that's what this is. This is not a webinar that is targeted at engineers and architects that have been dealing in great detail with noise control issues in building design for many years, and you're looking for a highly technical discussion. That's not what this is. This is targeted at all of the members of the building design team. You're, I'm sure, aware that from time to time, noise is an issue in building design, but my assumption is that that's about the extent of your knowledge up to now. So this will just give you a little more in-depth view of noise control. Now let me see, I need to figure out how to use my controls here. Okay, there we go. These are kind of the chapters in the book, the way I'll be chopping up the information today. Some introductory remarks, and then some comments on the basic fundamentals of physics underlying acoustics or noise control. Chapter 3 is noise criteria. In other words, this is your target, so to speak, in building design. You want to have a certain noise or sound environment in certain spaces in your building. Chapter 4, some sound distribution indoors. In other words, I will, in general, I'll be talking about a noisy room and a quiet room. And what you want to do is to design the building so that the people in the quiet room are not disturbed by the people in the noisy room. So the noisy room is where the sound comes from, the source, and the receiving room is the room where the people are that you are concerned about not being disturbed. Sound isolation between rooms, we'll talk about that because that's what you're doing, is you're acoustically isolating the noisy room, the source room, from the receiving room. I have a few brief comments on sound propagation outdoors, outside of a building. Not a lot of discussion there because of the amount of time that we've got. Airborne sound control, that's just a few comments on things that may need to be done for the benefit of the people in your building, separate and apart from things that you do in the design of the building. So that's kind of how we'll be looking at things today. Okay, here by way of introduction is a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight-ahead designer, cranking out drawings and specs for the construction of buildings and related infrastructure. I did not spend my whole career worrying about noise control or acoustics, this sort of thing. I have been a broadly based designer, and I got registered in a few different things along the way. And the hang on just a second, I want to check my controls. Yeah, I'm doing okay here. So I have not been doing up to my elbows in noise control and sound and acoustics and that sort of thing. I got registered, as I was starting to say, in a few different things. I'm basically a mechanical engineer. That's my degree and my first registration. So straight ahead designer. And then after the 35 years, why, for an additional 9 years, I was in what might be called the public policy arena. And I was a principal staff advisor to the California legislature on infrastructure and capital outlay issues for 9 years. So that's what I've been doing. These are the learning objectives here. You're welcome to review them at your leisure. I'm not sure. I think you can get a copy of these PowerPoints from PDH source. Check the website and follow the instructions, and you may be able to download a copy of these PowerPoints. This is not a textbook or a design manual or anything like that, but these PowerPoints may be of some value to you for future reference. Okay, so here we go. Some introductory comments. I want to introduce right up front, along with what we're talking about today, which is noise or acoustics or sound, another physical phenomenon, which is vibrations. And these are companions. And they both originate with something vibrating. It's might be a person singing in a room, in the source room, or playing the violin, or banging a drum, or a piece of machinery that's running, and the vibration of the vocal cords or the violin string or the piece of machinery is what causes sound and vibration. And the kind of the distinction between sound and vibration is that sound is perceived through the eardrum and by the receiver. But vibrations are perceived by the receiver through his fingers and toes. He feels it. And generally speaking, the vibrations are at a lower frequency, and sound is at a higher frequency, generally speaking. And the sound is by and large a through the air phenomena. In other words, this in the source room, the violin string is vibrating, and it sets into a vibrational mode air molecules that are adjacent to the violin string. And those vibrating air molecules, this is a way to visualize what we're talking about, the acoustical energy, the vibrations of the molecules. And one molecule bangs up against another molecule, and that chain continues through the air until it gets to a barrier between the source room and the receiving room. The barrier, typically in building design, is going to be a wall, floor, ceiling, some solid material. And the vibrational energy from the air molecules in the source room are transmitted to the barrier, the wall starts vibrating, you might say, which then sets the air molecules in the receiving room into the vibrational mode. And from molecule to molecule, it moves and finally gets to the eardrum of the receiver, and it the brain, and then the eardrum is set into a vibrational or acoustic energy mode, and the brain perceives this as sound. And it's not completely a through the air process, because the sound does get transmitted to a lesser degree through the solid materials in the building, the wall, floor, ceiling. The vibrations in the source room, say you've got a piece of equipment like a fan in a fan room, and the fan is running and is vibrating. And the vibrations are, in the case of the vibrations, they're transmitted more to the solid members of the building, the floor deck, the columns, the beams, etc., etc. And that vibrational energy is transmitted from the source room to the receiving room, and the receiver, the human being there, feels it in with his fingers and toes. So sound and vibration are companions, and the distinctions are that the sound basically is perceived through the eardrum, whereas vibrations are perceived through the fingers and toes. And the vibrations tend to be at a lower frequency. We'll talk more about frequencies as we move forward here. Okay, there are certain qualities of sound that it's important to keep in mind, or to understand, have a feel for. One is the level or magnitude of the sound. And the way to visualize this is think of the controls on this little rascal are, boy, these, hang on just a second, the controls are not very user-friendly. Hang on just a minute while I play around with this and try to get to the right slide. Let me see now. Why? Hang on. Well, gosh, this is really driving me bonkers here. Stick with me here. I'm having a difficult time with the slides. Okay, now I finally found what I need to find. So let's get back here. Okay, these characteristics of sound that are important to have an understanding of. The first is level or magnitude, and the way to visualize this is think of a sinusoidal curve going up and down and up and down and up and down. And this sinusoidal curve represents acoustic energy, you might say. And so if that sinusoidal curve is has a high magnitude, goes way up, way down, way up, way down, that is a loud sound. So the magnitude or level is high. And if the sinusoidal curve is just going up a little bit and down a little bit and up and down and up and down, that's a quiet sound. So that's a point to keep in mind. Sound has a characteristic of magnitude. And of course, this isn't new to you, you know this. Another characteristic is the frequency of the oscillations of this sinusoidal curve. So if the oscillations are very rapid, up and down, up and down, up and down, up and down, that is a high-pitched sound. And if the oscillations of the sinusoidal curve are slow, up, down, up, down, up, down, that is a low bass type of a sound. Now, so that's an important characteristic to keep in mind, and we'll talk more about this and why this is important as we move forward. Another important point to keep in mind is what's called the spectral content. Because in the real world, you almost never have the opportunity to hear a pure sound, just at a single frequency and with a single level or magnitude. What you hear is big bundles of sounds. In other words, a whole bunch of air molecules are impinging on your eardrum. Some of them they have a high magnitude, some a small magnitude. Some of them have a high frequency of oscillation, others a low frequency of oscillation. And it's this spectral content, this characteristic, that allows us to do things like speak and sing and so on and so forth, and listen to music. And it's just one of those marvelous things that the brain does, is allows us to vary just instinctively the vibrations that our vocal cords produce. So spectral content at any point in time, any sound you're hearing is actually a whole bunch of sounds all together. And along with this is the point to keep in mind is that this bundle of molecular energy that you're perceiving varies with time. At one point in time, there's one bundle of sound that's hitting your eardrum. An instant later, it's something completely different. And again, this is what allows us to speak and to listen to music and to play a violin and so on and so forth. So these are important basic characteristics of sound: level or magnitude, the frequency, and then the spectral content, the idea that that you never hear in the real world a pure sound of just a single magnitude and a single frequency. You're hearing big bundles of sound, and they are varying with time. Now, the sound is measured in terms of decibels. That's the unit of acoustic energy. And it is determined by equation 2-1 based on the sound power that you are perceiving with your eardrum. Decibels is equal to 10 times the log of P1 over P2, and the P1 is the sound power that you are perceiving at an instant in time, and the P1 is the sound power that you're perceiving at an instant in time. P2 is a reference sound power, and what that P2 is the a sound power that is just barely perceivable by a young, healthy human ear. And the and what is that sound power? It is 20. It is it is 20 decibels. Well, actually, that's not the best way to state it. It's the sound power that the young, healthy human ear perceives is let's get to the right slide here, is it's there we go. It's 20 micropascals. So that is the reference pressure, because that is the pressure that is just barely perceivable by the young, healthy human ear. And so the sound, the decibels, is the ratio of the sound pressure being perceived by your eardrum over the 20 micropascals. And that is the definition of the sound pressure and the decibel. So let's move forward. This is kind of extraneous or not terribly important at this point in time, but the way the sound pressure level is noted in text, it's usually abbreviated SPL, and the notation in formulas is L sub P. And the sound power is defined as L sub W, which is 10 times the log of the sound power to the reference sound power. The power, the reference sound power that is barely perceivable by the young, healthy human ear is 10 to the minus 12 watts. And so that is the reference pressure, so or power. The power that's being perceived by the eardrum divided by 10 to the minus 12 watts. So that is the definition of the sound power level. And again, with the abbreviations, power is abbreviated PWL in text and L sub W in formulas. The only reason this is of any significance is that the words power and pressure both begin with P. So a point to keep in mind is that the sound power in the real world cannot be measured. It's calculated. And the reason is, if you visualize a point source of sound, it's radiating the sound out in a three-dimensional global 360-degree type of a configuration. So the measuring device that would be measuring one of these power vectors would be measuring one level at one location, and moving it would be at a different location. And you're familiar with this in the real world, like railroads engines when they're coming down the track, when the horn is sounded when you're in front of the engine, it's very loud, but when the train passes by, then you're behind the sound and it is much lower. And there are all kinds of examples of that in the real world. Okay, the sound intensity level, should you want to calculate it. And in building design, it's unlikely that you're going to have occasion to calculate sound intensity level for any reason. But if you did, you would be using equation 2.9. Sound intensity is the power per unit sound power perceived per unit area, like per unit area of the wall separating the source room from the receiving room. And the equation that you would be using is equation 2.9. The sound intensity is 10 times the log of the sound intensity being perceived to the reference intensity, and that reference intensity is 10 to the minus 12 watts per square meter. And because that is the sound intensity that is just barely perceivable by the young, healthy human ear. Okay, let's see, I don't think we need to go into that. Let's talk briefly about vibrations here. You've got a source of sound and vibrations in the source room in the building, and the calculation of the vibration level is analogous to the calculation of the sound pressure in decibels, and that would be using equation 213. The vibration level in decibels is 10 times the log of the square of the ratio of the vibration level being perceived to a reference vibration level. And we're not going to spend time talking about vibrations here. Okay, now that's a very brief outline of decibels, how you measure sound. And in building design, what you are doing is measuring the sound in the source room or noisy room, and you want to reduce that sound power or sound pressure to a level that is consistent with what your human being is doing in the receiving room. Is the human being in the receiving room trying to sleep? Is this a hotel room? Then you want to have a nice quiet environment for the receiver. If the human in the receiving room is working in a shop type of environment, more noise, sound can be tolerated by people, so you can have a different sound environment that is acceptable. Now, frequency is important here in noise control in buildings and in talking about what people perceive. The human ear perceives sound in the frequency range from around 50 hertz. 1 hertz is, of course, 1 cycle per second. Or one so 50 hertz is roughly the lowest sound that the human ear can perceive, and then the highest frequency sound that the human ear can perceive is around 15,000 hertz. And that's a very high, squeaky, hissing type of a sound. So if the sound that is being produced is outside of that 50 to 15,000 hertz part of the acoustic spectrum, the human ear just doesn't perceive it and isn't bothered by it. Dogs apparently have a broader range of frequencies that their ears are sensitive to, so they might start barking if they hear a sound that is outside of that 50 to 15,000 hertz spectrum. And within that spectrum, as far as humans are concerned, the portion of that spectrum in which the human ear and brain are most sensitive to sound is the 500 to 5,000 hertz part of the spectrum. So sounds within that part of the spectrum, 500 to 5,000, those are the sounds that humans are most sensitive to and potentially most annoyed by. So below 500 hertz and above 5,000 hertz, between say 50 and 500 hertz, yes, the human ear perceives them, but the brain just doesn't pay much attention to them. From 5,000 to 15,000, yes, the human ear perceives them, but it isn't too bothered by them. So frequency important as far as humans are concerned. And of course, in building design, that's what we're concerned with as humans. So the human ear perceives sound between around 50 to 15,000 hertz. And in the 500 to 5,000 part of the spectrum, they are, the human ear and brain are most sensitive to sounds of those frequencies. Now, let's move forward a little bit here and introduce the concept of octaves. Now, this is the concept of octaves is has been developed for typically musicians and things like that, for the way they work with sound. It's not terribly important in building design, but nevertheless you should be aware of it. And the what the octaves are is this frequency spectrum is chopped up into the what are called octaves, which you see in this table. And down at the low frequency, the lowest octave extends from 11 to 22 hertz, and it is centered at 16 hertz, and so that is called the 16 hertz octave. And down through the table here, the highest octave that is defined is from 11,360 to 22,720, centered at 16,000 hertz, and that is referred to as the 16,000 octave. And these octaves are then further, for reasons that are not typically relevant in building design, are divided into thirds, as you see in the table. Now, let me stop here and move to the side for a moment. There is one area of building design where consideration of octaves and this more definitive look at sound is important, and that is if you have a space in the building that is being used for something like a concert hall, lecture hall, that sort of thing. And in that kind of a space in a building, the source and the receiver are in the same room. You don't have the source of the sound in one room making noise, and you don't have the receiver in another room. And so the source and the receiver are in the same room. The source is up on the stage playing the violin. The receiver is the sitting out in the audience. And the acoustic challenge in a space like this is the fidelity of the sound. You want the receiver to perceive the sound exactly the way it's being produced by the violin player on the stage or the speaker on the stage. And in this kind of a space in a building, the major bugaboo, if you will, is echoes. You have the source up on the stage playing the violin, emanating sound in this 360-degree global type of a configuration, and some of that sound shoots over and bangs off the wall, or it bangs off the ceiling, and it ricochets down to the receiver sitting in a seat in the audience. And so you get distortions with echoes like this. There's a slight, tiny difference in time between the sound vector that goes directly from the source to the receiver and the sound vector that shoots off, bangs off the wall, and bounces back to the receiver. And this challenge in building design basically is one where you need to call in an expert in acoustic design of these kinds of spaces, because a great deal of what is done in the design of a space like this, where the sound fidelity is driving the design. A great deal of this has just been learned by trial and error, literally over centuries. And in general, the concept is that you want to tend to use soft finishes in a space like a concert hall or a lecture hall. So soft finishes on the walls, perhaps drape type fabrics on the walls. In a typical office building, you have these suspended acoustic tile ceilings, and they are a soft material and mitigate and prevent to a significant degree the echoes that might otherwise occur in an office space and be distracting for workers. Carpets on the floor, soft material. That's why, as an example, anytime you go into a concert hall or a lecture hall, there's always carpet on the floor. It's there for aesthetic reasons, certainly, but it is also there for acoustic reasons. And the chairs in a concert hall typically are made of soft material, and they absorb quite a bit of these echoes and assist in maintaining the fidelity of the sound that is perceived by the receiver. And actually human beings, their bodies sitting in the seats in a concert hall, they absorb quite a bit of this acoustic energy. And so the sound that would be perceived in an empty concert hall is different than that which would be perceived in a concert hall that's full of people. The point is that this is a complex undertaking, and one where, first of all, you're probably not going to have a lot of occasions to design these kinds of spaces over your career, but if you do, you need to call in an acoustic specialist. What you, as a run-of-the-mill building designer, are concerned with is the reducing the sound in the source room to a level in the receiving room that is compatible with whatever the human being is doing in the receiving room. We'll be expanding on this as we move forward here. Sound decibels, it's a measure of the pressure of the air molecules on your eardrum. So where do you get started in routine building design from an acoustic standpoint? Now, by the way, I'm talking now in these illustrations about a source room and a receiving room. The quote source room can actually be outside the building. It can be a noisy freeway, and you are concerned about the sound environment inside the building, in an office or in an apartment, that sort of thing. So in run-of-the-mill building design, you need to determine the level of the sound that is being produced in the source room. And you do this quite simply in the vast majority of cases using a simple little instrument or device, a sound level meter. These are a very common type is a handheld device, and you go into the source room and using your sound level meter, you measure the sound level with the sound level meter. Now, when you walk into the room and start measuring sound, the sound level meter has a dial on it with a needle, and it bounces around in response to the sound that is perceived. And this illustrates for you quite clearly the temporal or time variation of sound levels. One instant, it's one sound power level. Another instant, it's something entirely different. And so what you've got is the sound level that you're measuring is bouncing around, and you can't read anything in any meaningful way. And so these sound level meters are, let's get over here, they are constructed with acoustic filters in them. And so the one of the knobs on this sound level meter there are two levels, two knobs, pardon me, on the typical sound level meter. One is labeled ABC. And what that does is it filters out a certain percentage of the sound at certain frequencies. And like as an example here you see these three curves drawn. The vertical axis is the decibel level relative, and then the horizontal axis is the frequency. And the A curve that you see there, if you get down into the lower frequencies, like say below 500 hertz, you see that the filter on the A setting on the sound level meter filters out or discards a certain percentage of that sound. And the reason is that the human ear is not, although it perceives that sound at those low frequencies, it's not too bothered by it. So the sound level meter filters that out, a percentage of that out, and discards it. Then between 500 and around 15,000, again, looking just at the A curve, the sound level meter does not filter out very much of that sound, and it records it. It's sensitive to it. And then above about 15,000 hertz, the sound level meter, the curve doesn't even go to those really high frequencies, but the sound level meter ignores all of the sound that is produced above about 15,000 hertz. So that A curve that you see there is mimicking the human ear. In other words, it's ignoring sound to a significant degree below 500 hertz, and it is measuring a sound between 500 and 15,000 hertz because that's the part of the frequency spectrum where the human ear is most sensitive. And then above 15,000, it just discards it. The B and C curves are different. They are flatter. They do not discard as much of the sound below 500 hertz. And so they are not mimicking the human ear. They are used for different kinds of measurements that are more specialized. And so you've got this knob here that has ABC settings on it on your sound level meter. and you're in the source room. And you will, in a typical building design situation, you will set that uh, knob that's on the A setting to measure the sound in the source room. The let's I'm going through quickly some slides here dealing with uh, sound and its wavelengths. We're not going to get into that in talking about building design. This tends to be something that is of significance if you're designing like mufflers for mechanical equipment, things like that. And so we're going to skip over that. Let's see, I'm looking at the clock here, and we are where we need to take our first 10-minute break. So let's do that. So we've looked at fundamentally how you define sound in terms of decibels, and we're now in the source room measuring the decibel levels of the sound that is being produced by the source. So let's take a 10-minute break now and come back at 2 minutes after the hour, and we'll pick up from here. So I'll see you all in 2 minutes, 10 minutes, pardon me. Okay, let's resume here. You're in the source room and you are measuring with your sound level meter the loudness of the sound that is being produced. And you have set your sound level meter, the ABC knob on the A setting, and that is will result in the sound level meter measuring the sound in a manner that is most representative of a human ear. And then the second knob that you've got on the sound level meter has two settings, fast and slow. And this sets the sampling rate for the meter. In other words, on the slow setting, the typical sound meter will sample or measure the sound being produced once each second. And if it's set on the on the fast sampling rate, it will be measured 8 times per second. And the this again is done to accommodate the reality that the sound is constantly varying as it's being produced. And the if it was set on the fast setting, this knob, the needle would be bouncing around like crazy, and you couldn't read it in any meaningful way. So this knob, typically, you're going to set on the slow sampling rate. And now the needle on the sound level meter is readable. And you now read the meter, but again, that needle is still bouncing around, moving around quite a bit. And so there is a second sampling rate that comes into play, and that is the rate at which you, the engineer or architect, read the meter. And you will do this, you will read the meter maybe once every 5 seconds, once a minute. It all depends on why you are measuring the sound. And there is an ASTM standard that tells you if you are measuring this kind of sound like freeway traffic, you should sample the sound level meter at such and such interval. And if you're measuring a different kind of sound, a fan in a fan room, you will sample the sound. You should sample the sound at a different frequency. And so that's what you do in measuring the sound level. If the procedure you're using says sample the sound every 30 seconds, you have your watch and you look down, you read the sound level meter at that instant in time, wait 30 seconds, read the sound level meter again, and then write all of these readings down, and you read them for the period of time. Hang on just a second, I need to do something here. Got an arborist working on the trees outside my office here. And so you write all of these readings down, and you then, using the ASTM methodology that is recommended, you blend them together by averaging them or taking the median or something like that. And what you end up with is a single number in units of decibels, which represents the sound being produced in the source room. And this obviously is an approximation, if you will, but over many decades, this has proven to be a workable way to approach sound and acoustics in building design, with the exception of, as I already said, if you're dealing with a space like a concert hall or a lecture hall, that's a different challenge. So that's something different. So you've now measured the loudness of the sound in the source room. With humans, the human ear will perceive very faint sounds down in the range of around 0 to 10 decibels. And when you get over about 80 decibels, those are very loud sounds, and the long-term exposure to sounds that are that loud can often lead to damaging the human's ears, eardrums. And so sounds above about 80 decibels are harmful. And over 100 decibels, that's going to result in probably in pain for the hearer. So let's okay, and now let's look quickly here at this table that's not terribly clear, but it's what it is. This gives you a feel for how a human responds to changes in sound level. If you have a sound and it is reduced by around 3 decibels, the human will say, yes, I can perceive that that change, the sound changed. If you go through and do the arithmetic, the actual acoustic energy loss with a 3 decibel reduction is around 50%. If it's the decibel change is 10 decibels, the human would perceive that as about half as loud, even though it's only a 10 decibel change, and so on through this table. And this, again, is just to give you a feel for how the human responds to changes in the sound level. We're now vibrations. We aren't going to get into vibrations other than one point that's worth it can be important in building design, and this is resonance. Every structural or mechanical system or element has a natural frequency that theoretically can be calculated. And that is one single frequency. And if the mechanical system, like say a beam in a building, if it is subjected to a forcing frequency of vibration that is at the frequency which is the natural frequency of the beam, then the natural frequency reinforces the forcing frequency. The amplitude of the oscillation of the beam increases and increases and increases, and taken to its ultimate resolution, the beam would break. So the point is that with vibrations, an important consideration is to make sure that your forcing frequency is not the same as the natural frequency of the structural element or mechanical element that you are concerned with. You can get a copy of these PowerPoints and read this a little further. Here, one other point as far as the vibrations in a building design situation. A common issue is like a fan in a fan room. And the fan inherently is vibrating in there and bouncing up and down. And so typically with something like a fan or a compressor or something like that, you have it mounted on a frame of some sort. And commonly it is, that frame is then mounted on vibration isolators. Now, these vibration isolators can be just like a rubberized type of a pad, or they might be these spring type vibration isolators, which are just a spring inside of a housing, and the frame for the fan is set on 4 of these vibration isolators, and that isolates the oscillating fan from the structural elements of the buildings, the deck, the beams, the columns, this sort of thing. One thing you have to watch out for is, though, if your vibration isolators have a natural frequency that is the same as the forcing frequency, which is the speed of rotation. Let's see. Somebody's got a question. I've seen apps for smartphones to make them sound meters. Anything, if they're worthwhile or better in a real meter. I'd invest in a real sound level meter. They're not that expensive. Let's see, Quest is the manufacturer of the one that I used for a long time, Quest. And they're not that expensive, and you never know. You may start having some of these projects wander into your office, these acoustic projects. That was actually the case with my career. Career number 1, I was with a large public agency for 17 years. Then for 18 years, I had my own architectural engineering firm. And it was during that second career when, for whatever reason, just because we had a sound level meter, we started getting these sound projects for noise control inside buildings or outside. Anyway, getting back to this situation with the fan in the fan room sitting on these spring type isolators, one of the things you got to watch out for is that if the natural frequency of the spring isolators is the same as the forcing frequency, then the amplitude of the oscillation of the fan and its support framework are going to really be bouncing around a lot. There is a way to determine quickly if your isolators, though, are going to have the same natural frequency as the forcing frequency which the fan is imposing, and that's using equation 217. SD in this formula is the static deflection. So the spring isolator has a certain length, 2 inches, and in an unloaded condition, you put the fan on the spring isolators and they squash down to 1 inch, so you've got a static deflection of 1 inches. Plug that into this formula, and that tells you with reasonable accuracy the natural frequency of the spring isolators. So if and the frequency of the forcing frequency, the fan, is in the typical situation is the speed of rotation of the fan, and if the speed of rotation of the fan is pretty close to the natural frequency of the vibration isolators, then you've got a problem that's probably going to occur, and so you need to select a different vibration isolator. That's kind of an aside there. Again, the vibration isolator can be something as simple as a rubber pad. Okay, how close your forcing frequency is to the natural frequency of the spring isolators. If it's within a ratio of about 1.4, then that's the danger zone. If the ratio of the driving frequency to the source of the natural frequency of the mount is above 10, you're not going to have a resonance problem. Okay. You've now measured the sound in the source room. Now you need to go into the receiving room, and what is the noise environment that you want to have in the receiving room? Well, and that's in the building design situation. That's a function of what the people in the receiving room are doing. Are they trying to go to sleep? Are they working in an industrial environment? Whatever. And there are 3 quantities that have been defined. 2 of them are the ones that you'll use most of the time. There's something called room criteria, and we're not going to discuss that. The one that's important in defining the noise environment in the receiving room is the noise criteria, the NC. And that is supplemented by another criteria called a speech interference level if the human activity going on is one where 2 people in the source room need to talk to each other. And so the important one in defining the noise environment in the receiving room is the noise criterion, NC. And so these, what are called the NC curves, have been defined and used over many years and they look like this. They're defined in some ASTM standard. And these curves range from what's called NC15 up to NC70. And the number 15 or 70 nominally indicates the loudness that is acceptable in that space. And here the up at the top is the NC70 curve, and down at the bottom is the NC15 curve. And so looking down at the bottom curve, the NC15 curve, this curve says that if the sound in your receiving room, if you want it to be, if it's to be 10 decibels, say at 4,000 hertz, then that would be below the NC15 curve. If the sound pressure level at 500 hertz is 20 decibels, that's below the NC15 curve. So the NC15 curve is a quiet room. The NC70 curve is a noisy room. And above around NC 65, 70, around there, sustained exposure to the noise environments above NC 70 long term, there is the likelihood of hearing damage for humans in that space. So these curves have been defined over the decades, and obviously they are an approximation, but they work pretty well. And so as far as the receiving room is concerned, what you do is you select the NC curve that is consistent with the human activity going on in that receiving room. So what curve do you select? Well, this is a table that one very highly experienced organization uses. This is a Department of Defense design manual, and it relates the human activities to NC curves, and it this approach, which is reasonable and is applicable to all kinds of spaces. There's nothing military or defense or governmental or anything like that about this table. It's just good common sense engineering technical guidance, and it defines 6 categories of human activity. Category 1 is bedrooms, residences, hotels, motels, etc., where the primary human activity is sleeping, resting, relaxing. And so using this system, you would want to select for your receiving room an NC curve as your target of 20 to 30. The next category is a little bit different. It's auditoriums, theaters, etc., where the driving consideration is that you want to have very good listening conditions. And so you would select an NC curve of somewhere between 15 and 30 as your target. Category 3, you can tolerate a bit more noise in the environment, so but you still want good listening conditions. This would be private offices, classrooms, libraries, and for this kind of a human activity, you would select an NC curve of 30 to 35. Larger offices, cafeterias, stores, shops, restaurants, you still want to have fair listening conditions in category 4. And so you would select as your target NC 35 or NC 40. And category 5, you can tolerate a little noisier environment, but you still want to have moderately fair listening conditions. This would be shops, engineering spaces, laboratories. And so for that type of a receiving room, you would select the noise criterion of 40 to 50. And then category 6 is the noisiest environments in this system, kitchens, laundries, power plants, etc. Minimum acceptable speech communication, but no risk of long-term hearing damage. And so you would select an NC curve of 45 to 65, something like that. And that's your target for your receiving room. And this obviously is a kind of a coarse way to approach the setting of the acoustic environment in the receiving room, but it has proven to be workable over long periods of time, many decades. Now, the room criteria, we're not going to spend time on because it's, generally speaking, in day-to-day building design, it's not something that you would probably be using. The RC or room criterion curves look like what you see here. They're in a way kind of analogous to the NC curves, but the curves are different. So your NC curve that you select as your target, you then supplement that as appropriate with a speech interference level, which is a sound level that would potentially interfere with two people in the receiving room communicating with each other. And without going into the details of speech interference level, it kind of looks like is illustrated by this table here. You have, say, two people 10 feet apart and they need to communicate. And they can communicate in a normal voice in an NC environment of 48 decibels. They can communicate in raised voices in a noise environment of 54 decibels, very loud voices, 60 decibels, and so on and so forth. So this just gives you a feel for the speech interference levels criteria, which you would take into account if communicating between people who are in the same receiving room. Now, okay, you've gone into the source room and you've measured the sound that's being produced with your sound level meter and using the ASTM methodologies, and you come up with a single number that represents the sound being produced in the source room. Say it's 90 decibels. And you want to, because of the human activity going on in the receiving room, you want to reduce that to 40 decibels in the receiving room. So you need to achieve a reduction of 90 minus 40 or 50 decibels between the source room and the receiving room. And you do that by how you construct the barriers between the source room and the receiving room. And the barriers, of course, are typically in building design are the walls, ceiling, floor. Now, there is the way the sound, as I sketched out early on, moves from the source to the receiver. First of all, a certain amount of the sound will be absorbed in the source room just by virtue of distance. And you know this in the real world, that if there's a car honks its horn and it's just a few feet away from you, why, it's a very loud sound. But if it's several blocks away and the car horn honks, you hardly even notice it. So there is a reduction due to distance, a loss of acoustic energy just due to the distance effect. And but in building design, within a building, the distance effect, the distances are typically small, and so there's not much sound reduction due to distance, so you don't bother taking it into account. And any reduction that you do get due to the distance effect, you just accept it as a plus, a safety factor, if you will. There is also a certain amount of sound that will be absorbed in the source room by absorption. This is when there are soft type finish materials in the source room. The air molecules with the acoustic energy bang into these soft materials. The soft materials deflect on a microscopic level, and the vibrational or acoustic energy of the air molecules is reduced by absorption within the source room. And similarly, on the receiving room side, you also have some degree of absorption due to the distance effect between the barrier wall and the human ear. And then there is also a certain amount of that acoustic energy that is absorbed in the receiving room as a result of absorption with finished materials, carpet on the floor, things like that. But again, you don't bother in building design calculating that sound absorption on either the source room side or the receiving room side. It's small typically, and you just take it as a safety factor, if you will. And so the main tool that you have available to reduce sound between a source room and a receiving room is the barriers, the walls, the ceiling, the floors. And This is where the, let's see, I don't think we need to get into sound absorption coefficients. We don't have enough time for that. So I'm not going to go into that. From a building design standpoint, then your job is to design the barriers, the floors, ceilings, walls, between the source room and the receiving room, that will achieve the sound reduction that you want. You've measured the sound level in the source room at 90 decibels. In the receiving room, you want it reduced to 40 decibels. And again, these obviously are approximations, but they have proven to work very well in a very broad range of applications in building design. And so you want to design a barrier, a wall that will reduce the sound on the source room side from 90 to 40 on the receiving room side. Now, here we need to introduce an important consideration, and this is the building materials that you use to construct your barriers. The chipboard, the concrete masonry blocks, glass, et cetera, et cetera. And an important consideration is that of transmission loss. For a given building material, like say chipboard, chipboard will reduce the sound a certain amount at the at low frequency, at one frequency, say a low frequency, and something different at a high frequency. This table here shows you, illustrates this fact. You have different frequencies indicated from 125 to 4,000 hertz, roughly the part of the spectrum, the acoustic spectrum, where the human ear is most sensitive. And so you see, as an example of unglazed brick, has a coefficient of 0.03 at 125, a transmission loss coefficient of 125 at 125 hertz of 0.03, and at 4,000 hertz 0.07. So unglazed brick, a little better at the higher frequencies, reducing the higher frequencies. So anyway, all of these building materials have this characteristic, that their transmission loss, noise, sound transmission loss, is a function of frequency. So it's nominally it is a complex undertaking, but it has been simplified, and that has been by the development over many decades of the concept of a sound transmission class, STC. And this is a number that has been determined to represent the sound reducing characteristics of a given construction scheme, like talking about a simple wall, 2x4 wood studs at 16 on center with 5/8 chipboard one side and 1/2-inch chipboard, 2 layers maybe on the other side. That construction has been determined to have a certain sound transmission class rating, a single number. And how are these single numbers determined? They're determined by test, field or laboratory tests. And typically these tests are conducted by a neutral testing agency like Underwriters Laboratories. And so the way the industry has developed is that, say, the chipboard people want to be able to market chipboard to the designers of buildings, engineers and architects. And so they have a lot of different configurations for chipboard used for constructing walls between rooms. And they have just, over the decades, they've just gone to like Underwriters Laboratories and said, please test this wall construction and determine what its STC rating is. And the methodology that Underwriters Laboratories uses is an ASTM one that you can look up. And so Underwriters Laboratories tests that wall construction and determines that it warrants an STC rating of whatever. And the STC rating is just a single number. So and then the chipboard people incorporate this technical information in their marketing materials, and you as an engineer or architect just go to the chipboard catalog and look at the STC ratings of the different construction systems that you can select, and you simply select one. So in this simple example that I've been giving here, you would you've got a 90 decibel sound being produced in the source room. You want to reduce it to 40, so you simply select a construction scheme that will reduce that sound, an STC rating of 50. 90 minus 50 equals 40. So you've achieved your target there in this simple example. And many of the design situations that you are faced with in building design are pretty simple like this. They can be more complex, but a lot of them are pretty simple. And there are things that you can do to improve the sound reducing characteristics of a barrier like a wall. One of the things that you can do to improve the sound reducing characteristics is you can use staggered studs. So you've got your wall being constructed by 2x4 wood studs, 16 on center, but you offset them so that the chipboard on the source room side is attached to one set of studs, but the chipboard on the receiving room side is not attached to that set of studs, but to a separate set of studs. And so what you have done there is you have broken or increased the noise reducing characteristics of the solid material path of the sound, the acoustic energy, going from the source room to the receiving room. I said at the start that sound is primarily a through the air phenomena, but sound also does get transmitted through solid elements in a building system. So staggered studs. Another, of course, as you've probably encountered this already in your careers, another good way to improve the sound reducing characteristics of a wall is putting fiberglass bats, acoustic bats in the airspace between the studs in a wall. And that is because the acoustic energy passes, a certain amount of it passes through the airspace between the studs in the stud wall. If you put the acoustic bats in there, these very fine, light fibers absorb some of that acoustic energy. And so acoustic bats are or other types of fill material in the airspace in the stud wall is a way to improve the sound absorbing characteristics. And all of these different things that you can do, they have all been, essentially all of them have at one time or another been tested by underwriters laboratories to ascertain what the STC rating is of the improved barrier. Double stud walls is a further enhancement, better than the staggered stud walls, because the staggered stud walls, the plate and the cap on the wall are the same piece of wood that the studs are attached to. But if you use a double stud wall, then you have the studs on one side on one cap and plate and on a different cap and plate with the other studs. Another improvement that is marketed and is quite effective is flexible metal or sometimes plastic channels that are attached to the studs in the wall, and then the gyp board is attached to these flexible channels, not attached directly to the studs. And so these flexible metal channels or plastic channels will absorb a certain amount of that acoustic energy as well. So that is another improvement that you can make in the wall. There are other issues that crop up in building design. One point to keep in mind is that ductwork in air conditioning systems provide a pretty convenient path for sound to get from one room to another. And in particular, where this often crops up is in the fan room. The fans are noisy. Some of that fan noise can be transmitted through the duct system into the occupied spaces. So mufflers or sound absorbing lengths of ductwork are installed typically in the discharge from the fan. And sometimes the the ductwork is lined on the inside with sound absorbing fiberglass bats and that absorbs quite a bit of the sound from the fan room, and then keeps the sound reduced. The potential is reduced for sound to move from one occupied space to another occupied space. So, and keep in mind that in designing your barriers, the that with like a wall, if you need to have a noise reduction of say 50 decibels nominally, everything in that wall needs to have that noise reducing characteristic. So that includes doors and windows and things like that. So you may need to buy doors that are labeled as having an STC rating of 50 or whatever. And these doors, their STC ratings, or glazing systems STC ratings, they are all determined by test, Underwriters Laboratories again. So that brings us to kind of the end of our time here. And I'm flipping through these slides expeditiously. These tables that you're looking at here again illustrate how the transmission loss for a building material is a function of the frequency. So like here you've got hollow core concrete block walls. You see that at low frequencies, 31 hertz, and for various thicknesses, like an 8-inch concrete block wall at 31 hertz has an transmission loss of 29 decibels. At 8,000, it has a transmission loss of 57. And then down at the bottom, you see how these numbers using the ASTM methodology are blended together to come up with a single STC number that it is proven to be workable to just, if you have an 8-inch concrete block wall, it has an STC rating of 45, and that approximation is adequate for building design purposes. And then there's more of this kind of illustrative data for different construction systems. Okay, and we don't have time to get into sound propagation outdoors. So I'm going to need to bring things to a conclusion here. I hope this gave you a little bit of a feel for how you approach controlling noise and sound. By the way, noise is, and we're not going to take the quiz here online, noise is unwanted sound. Noise is sound, but it's unwanted sound. So, all right, with that, let me thank you very much for letting me chat with you. I hope this was about what you were looking for when you signed up for this. And with that, I'm going to just close things out and wish you to all have a nice rest of the day. So thanks a lot. Bye.